countermeasure most people come up with when they first hear about it is let's add noise. If you follow some of the threads that are on the OpenID list, some of the first things people said is, well, we'll just add random delays or whatever. And it sounds good at first. So you're looking at a graph and you're like, hey, it seems like we can do something about this. So let's start with the first. This is without noise. And then we add a bunch of noise for a certain number of samples. So we say, like, here's 500 samples with, I think you added like between 0 and 1.5 milliseconds of noise to this randomly. Sorry, 150 nanoseconds of noise to each of these. So on the order of the delta between them, we basically could double the value or add nothing to a value depending on the random choice we made. So as you can see, this distribution looks pretty random. And more importantly, you can't distinguish the black from the yellow, right? There's a lot of overlap where it's brown, but there's no clear distinguishing factor. But let's just take some more samples. So while still adding noise, we increased it to 1,000 samples. As you can see, the distributions are starting to look more like they did originally. And then we took 5,000 samples. Again, these still have noise added to them. But as you can see, the two peaks are starting to separate out clearly. There's kind of an outline of black on the left and an outline of yellow on the right. And then finally, with 10,000 samples, as you can see, you have almost identically to the original distribution. So adding noise does not do a good job of preventing timing attacks. It only requires the attacker to take a few more samples. A fix that we recommended to a lot of people on these mailing lists was a simple constant time compare loop. This used to be an interview question we would use, but since we revealed it to everybody, it's no longer an interview question. So this is in C, but the equivalent works in Python or Java or whatever. Basically what you do is you check the length first, and then if you go walk through all the bytes in the array and you just compare them and you XOR them together. If there's a difference between them, you'll get a non-zero value, and if there's no difference, you'll get 0. And each time you accumulate using OR. So the important thing about this code is that it doesn't generate any conditional branches that are varying based on the secret data that you're comparing. And there's a few things about this. The first thing we got back from a few people was, hey, this is a lot slower in some of our interpreted languages. The particular example someone used was .NET. And what they were saying is, hey, in .NET, a normal comparison devolves to C memcomp. And this particular loop implementation, of course, is implemented in bytecode, and so isn't quite as fast. They found it was about, I think, 10 times slower than a memcomp. But if you remember, the memcomp probably is not your bottleneck on your server. If it is, you're handling a ton of requests. You probably need another server. And then second of all, it's probably better to not be exploitable than to be a little faster and insecure. Absolutely, yeah, definitely. The HMAC hashing operation takes a lot more CPU horsepower than the comparison. But depending on whether that's implemented in native code or not, it may vary. So that could be a problem, and it could affect some implementations, and it's worth some investigation, but we don't think that's a good enough reason not to fix this bug. So OpenSSL. I was set to put some slides in here, and I was trying to decide whether or not to put these in or not. So I decided to tell the story instead. Yes? Yes. By the way, we're going to have questions answered at the end as well. Yes, Sun did fix their JDK implementation in update 17, I believe, or 18 of JDK 6. It's either 17 or 18. And they changed their message digest to equals to be basically that code that we showed. So OpenSSL. So we went after like OAuth and OpenID, and we found nearly every implementation. There's dozens out there, first of all, so it took forever to review them. And we found nearly every implementation had this timing leak in them. A few people had actually a year ago, when we had originally given a talk based on timing attacks at Google, talking about the Keysar flaw and others, they had originally fixed, I think it was one of the Java OpenID implementations. Can't remember which one it was, but anyway, so they fixed a few of them. So some of the maintainers took it upon themselves to fix that, and that's great. A lot of other people said, it's too small a difference, we don't care about it. So that continues to this day. So the story of OpenSSL. So OpenSSL has this thing called session tickets. It's in TLS 1.0 spec. It's an extension. What happens with SSL is you have this thing called your session state. You can do things like resuming sessions. And resuming a session is basically, what you do is, instead of doing all that key exchange and heavyweight public key crypto operations, you say, I as a client would like to use that same key that I negotiated with you, server, a few minutes ago. When you do multiple HTTP requests, for instance, with your browser, it will implement this SSL session resuming. And this is perfectly fine. It's perfectly secure. You're just saying, I want to use that key that I already know about. If either the client or the server don't actually know the key, so if one of them was trying to lie about this resume, they can just force a renegotiation back to a new key. So people wanted to optimize SSL, and in the TLS 1.0 spec, there's this thing called session tickets. So normally what has to happen is the server has to keep all this session state in memory or in a disk cache or somewhere, so that if the client decides to resume it within a particular time window, that it has the secrets available for it. And that's okay for normal servers. It's not that much data. It's a few hundred bytes, less than a kilobyte probably. But for embedded systems, this was a problem because they'd have to have lots of RAM to keep all these sessions around if they're being used as a server. So session tickets was is an optimization of that. What you do is the server takes the session state for the client, and after the client has negotiated a key with it, encrypts that with a key known only to the server, and then HMACs it also with a key known only to the server, and sends this off to the client. And the client has the option, if it supports this extension, of saying, hey, here's this session ticket that you handed me a few minutes ago. Let's reuse that session. And the server will say either, okay, I'll do it, or no, I don't like this result. For instance, if the HMAC doesn't validate, it's not supposed to allow the client to select that key. Well, of course, we went and looked at OpenSSL and found that they were using memcomp. So the standards see memcomp to verify the HMAC result of session tickets. And session tickets are enabled by default in OpenSSL as well. So we contacted them and actually said, hey, you might want to use this particular comparison loop. And it was about 3 weeks ago. And they said, no thanks. We think it's too small. And we said, well, it is very small. It is C. We found that the C variations was around 800 picoseconds to a few nanoseconds on our server. And we don't think this is exploitable over the internet for sure. Possibly exploitable in LAN situations, but mostly we don't know because these configurations are highly dependent on the particular servers and network that's involved. So as we found in our measurements, and as the Rice University researchers found as well, some configurations are extremely visible. We found a factor of 4 in our variations of the EC2 measurements, where we could actually see much smaller differences. So we suggested they fix it a few times, and they came up with various reasons why they didn't want to fix it. So today, it's still not fixed, actually. OpenSSL is unpatched, and it's an interesting challenge. We have not exploited it yet, but we'd be interested in seeing if anyone else out there can exploit it. Mozilla chose to fix this about in October of last year. So NSS is secure against this attack, and we hope that OpenSSL will eventually fix it. So let's see. Any questions? Yes? We haven't looked at GNU TLS. So we looked at NSS and OpenSSL and found OpenSSL hadn't fixed it, GNU TLS had. So based on this, there's a couple different attacks we think should be more successful against the OpenSSL HMAC verification. One of them is some of the branch target buffer prediction stuff, where if you're on the same server or if you're on the same EC2 server, this is something that you should be able to take advantage of as a side channel. It's very powerful, and it gives you intermediate results. We think that it may be a profitable way to go to measure the branch prediction of the HMAC compare loop. And we think that normal cache timing attacks probably won't be successful because the HMAC value is relatively small. It's about 20 bytes. So that tends to fit within a cache line. Whereas with AES, your tables are spread all over different cache lines. So AES and RSA are much more visible from a cache timing attack. So it'll be interesting to see what people can do. Yes? That's a very good question. So the question was, is the normal Unix password comparison function vulnerable to this kind of thing? And the answer is mostly not. So in the case of a plain text password, one of the things that we talk to some people about is they say, well, what about plain text passwords? And yes, of course, plain text passwords are definitely vulnerable to this kind of attack. You shouldn't be using plain text passwords for lots of reasons, but that's just another one. So for hashing your password and then comparing the hashes of it, what's nice about that is being able to do a timing attack doesn't help the attacker in that situation because it's iteratively exponentially more difficult to create a given hash to match the particular value on the server. So for the first few bits, it's very easy. It only takes 256 tries at most to collide in the first 8 bits. But after that, then it takes another factor of 2 to the 8 multiplied by that and accumulate until ultimately you're doing about 2 to the 160 work for SHA-1 or equivalent for whatever cipher you're using for your password hashing routine. So that becomes infeasible. There is a combined attack that was a pretty interesting idea that Tim Newsham came up with that was based on attacking Unix password hashes. And what it is, it's a combined online and offline attack where you use, because the salt, for instance, if you want to do a partially online attack against a password, you can use a timing attack to gain information about the salt and some bits of the hash, maybe the first 8 bits. And at that point, you can do offline analysis and brute forcing of the password. And if you find that it doesn't hash to the same 8 bits in the first byte, then you reject that and don't even bother sending it to the server as a candidate test. And this can help you eliminate, if you're doing a dictionary attack, for instance, large quantities of your dictionary. But it doesn't reveal the password directly. Yes? Oh, okay, any other questions? Yes? It was message digest equals. So in the case of HMAC, the message digest is the underlying primitive. And that was fixed in Sun's update 17. But not every distribution has rolled out this new version, so there are still a lot of vulnerable implementations. Definitely. So of all the languages we looked at, Java's comparison functions were by far the most visible in terms of timing deltas. They had from around 43 to 45 nanoseconds average byte differences, and then sometimes much greater. For instance, at 800 megahertz, we saw between 120 and 180 nanoseconds, which was visible from most local configurations we could come up with. Yes? That's a good question. So he was saying, is there maybe a way you can mislead the attacker by supplying fake hash values or whatever? So it's probably best not to build something so complicated, but I can think of some ways that might be helpful. For instance, if you're getting numerous HMAC validation problems, say more than one, from a given host, then something weird is going on. HMACs don't just fail to validate. Either your server has major memory corruption problems, or an attack is going on. Those are the only real 2 things that could be happening. And in those cases, you really want to know about it. So you should probably log it if you get something like this, because it should almost never happen. And then, yes, you could say if one IP address, for instance, is sending repeated incorrect HMACs, you could just compare it against garbage data by hashing something somewhere and rehashing it or whatever. And at that point, they would never succeed. And that might be good for honeypots, for instance. Yes, of course. You just compare it against, like I said, a hash of some garbage data somewhere,